Hi, we're going to take some notes on 4.4 sinusoids, graphs of sine and cosine. Now, hopefully, if you remember your 12 basic functions, you know what sine and cosine look like as graphs. We're going to take a moment to kind of talk about how we get there. So we are going to make two charts, just like you guys did way back when you were learning how to graph functions, where you said, okay, I'm going to make a table, x, y, x is 1. In this case, y would be 5. X is -1, y would be 3. We're going to do the same thing for sine and cosine. And the only thing I want to kind of note here is that our theta, our angle measure here, is going to be in terms of radians. So I am going to give us some radians here. So this is going to be theta, and this is going to be f of theta, x and y. Let's consider the angle measures of 0, pi over 2, pi, 3 pi over 2, and 2 pi. So to find our y value here, I need to find sine of 0. If you take a moment to find your unit circle, we can look at that. Remember, sine is y, so we are looking at sine of 0 degrees. We're right here. Sine is y. The y value here is 0, so that means sine of 0 is 0. Sine of pi over 2, we can go back to our unit circle. Pi over 2 is that 90 degrees, right? Y value of this point is 1. So sine of pi over 2 is 1. If you want to pause the video, take a moment to find sine of pi, sine of 3 pi over 2, sine of 2 pi. That would be great. Otherwise, when you look on your unit circle, you should see 0, -1, and 0. Now let's consider our cosine. So again, we're looking at theta, and in this case, g of theta, which is cosine here. We're going to look at the same angle measures, so 0, pi over 2, pi, 3 pi over 2, and 2 pi. And again, we're doing the same thing, right? Cosine of 0, sine is y, cosine is x, so that means this would be 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2, 0, and cosine of 2 pi, 1. So now we actually have a bunch of points that we can plot on these graphs. And before we get to actually graphing these, we do have to get our x and our y axis all squared away. So we know that this is our x values, or in this case, theta, and this is f of theta, otherwise known as, in this case, sine. If we look at our x values, our theta angle measures, they go from 0 to 2 pi. So I'm going to simply put 0 is still the origin, right? 0 is still here. And I'm going to say here is 2 pi, which means pi is halfway. Pi over 2 is halfway between 0 and pi. And then 3 pi over 2 is right there. And again, 0 is always 0, the origin. On my y-axis, I notice that the highest it goes is 1 and the lowest it goes is -1. So I really don't need a very big scaling here. I'm going to say this is 1, down here, -1. Now I can plot my points. Looking at your table, we have the point 0, 0. We have the point pi over 2, 1. We have the point pi 0, 3 pi over 2, -1, and 2 pi 0. And if you remember what the graph of sine looks like, hopefully you do, I can see its shape with just those points. We've got our lovely sine curve. And I do know that it continues in both directions forever. Let's pause your video and try and draw the graph of cosine. I am going to take some time right now to draw out all the pieces, but I'm going to move a little quicker. So if you want to skip ahead to where you see this all drawn out, you can definitely do that. Again, we notice the curve that we are familiar with, and it continues on in both directions forever. So we've got our graphs of sine and cosine, and I want to talk about a couple things. Let us consider our domain and range. Domain for these functions, if you remember, because they go on forever and ever in both directions, is going to be all real numbers, negative infinity to positive infinity. Negative infinity to positive infinity. And range here, the y values, the f of theta, g of theta, notice that the highest this function gets in both cases is 1, and the lowest it gets is -1. They do include 1 and -1, so our range is from -1 to 1. These 5 points that we plotted are super important. They would be ones that you should really know, because as we continue in this section, we are not going to be just plotting sine or cosine. We're going to plot transformations of these. So these are kind of the most important pieces to know. And I don't think I talked to you guys about this when we first did our 12 basic functions, but if you are someone who sometimes gets sine and cosine mixed up, which is fair because they are very similar, I'm going to give you one small thing to remember. So right now I'm drawing both functions and I'm not going to tell you which is which, but if we look just around the origin and we kind of draw what we see just around the origin, and this is like a silly thing, but notice that this function kind of makes an S. This is sine of theta. And if I draw just around the origin here, this kind of makes a sideways C. This is cosine of theta. If that helps you remember it, great. If you already knew these functions, that's even better. Let's talk about what a sinusoid is. It's not like a dinosaur, even though that kind of sounds like it. A function is a sinusoid if it can be written in the form a times sine of bx plus c plus d, where a, b, c, and d are constants. We want to make a note that a is not equal to 0 and b is not equal to 0. If either of those were, it would not be a sine or cosine graph. And if you notice, both sine and cosine are sinusoids. They can be written in terms of sine. If we go back for a quick second, these graphs are exactly the same. They are just horizontal shifts of each other, right? If I took this red graph and I moved it over to the left a little bit, it would be cosine. Or if I took cosine and moved it over to the right a little bit, it would be sine. That's why both of these functions are considered sinusoids. Let's talk about a couple super important characteristics of these graphs. The first is the amplitude of the sinusoid. The amplitude of a sinusoid is equal to the absolute value of A. The amplitude is this value right here. Now, if we think for a moment, this would be like if this was my original function and I had y is equal to 4 times x squared. Think back. How does this 4 influence this function? If you are thinking in your head, hey, this is going to be changing the y values, this is a vertical stretch or shrink, you're correct. That's exactly what this is. Changing a is going to make the function vertically stretched or shrunk. It's a vertical, maybe I'll say that, vertical stretch or shrink. Graphically, our amplitude is, there's two ways we can write this. Either I can say it's half the height of the full wave, or you can kind of consider it as the distance from the maximum to the midline. What does this look like graphically? Let me show you. So if we have y is equal to sine of x, I know just offhand that that is our parent function, right? It goes up to 1 and down to -1. But if I consider the graph of y is equal to, let's say, 4 sine of x, this is going to be a vertical stretch. It goes all the way up to 4 and down to -4. 4 up here, -4 down here. Because remember, vertical changes on the y, act how we would expect them to. So this 4 is going to basically stretch it much higher. So we can consider half the height of the wave. Well, notice the height goes from +4 to -4. The total height is 8. Half of that height is 4. Or we can consider the distance from the maximum, 4, to the midline. That distance is also 4. Thus, the amplitude of this graph is 4. The second thing we're going to talk about is the period of the sinusoid. And I'm going to talk about first the definition, and then we'll look at what it is like here. But if we think of, and I can say this because who cares, if you think of your period, it is something that comes in cycles, right? It repeats after a certain number of times. That's the exact same definition for the period of a sine or cosine function, except for we make it a little bit fancier. The period is the length of time, and I'm going to put that in quotes because it's not officially time, but the length of time it takes for our function to repeat. So let's go back for a second and just look at the graph of, let's go with sine. If I look here, notice this dark red curve is going to repeat itself starting right here. We're going to see an exact, so sorry about that. We're going to see an exact replica right here or to the left of it. So how long, what length of time, and I guess we're going to be talking in x, does it take for this red piece to repeat itself? Well, if it's starting at 0 and going to 2 pi, the period here, the length of time it takes to repeat itself is 2 pi. Thus, if we look at the quote-unquote regular period of a sine or cosine function, the period, cosine is 2 pi. That is of the parent function. Now, if we think of this graphically, how we've been doing transformations before, to change how long this thing takes to repeat itself, we would want to do a horizontal shrink or stretch, right? I can't physically do it on here, but if I took this thing and I squished it horizontally, the period would be smaller. It would repeat itself more frequently. So that's why, if we look at our definition here, the period of a sinusoid is equal to 2 pi divided by whatever this b value is. Remember, if this was our original function and I said y is equal to 3x quantity squared, you would think to yourself, the 3 is touching the x, it is a horizontal change, and specifically, it's the opposite of what we'd expect, a horizontal shrink. Same thing here. If we have y is equal to sine of 2x, this is going to change the period by shrinking it. This graph will not go all the way to 2 pi. The period here is 2 pi divided by b, in this case, pi. So instead of the graph that we saw before that looks like this function is going to repeat itself from 0 to pi. So it's going to be squished like that. Again, this purple guy right here is just sine of x. This red guy is sine of 2x. Last definition is phase shifts, which really just means, are we moving this function to the left, to the right, up, or down? And so we have to be a little careful here because we actually want to write that original thing as a factored version. So we really want to factor out b. A times sine of b times the quantity x plus, I'm going to say h here. H is like C divided by B, basically, plus D. And if we think back to what we remember about our left, right, up, and down, hopefully you remember adding it to the outside is our vertical shift up or down. Adding it to the inside is our horizontal shift to the left or to the right. A vertical shift would look like this. Sine of x plus 1. That graph has been moved up 1. And a phase shift would look more like y is equal to sine of x minus pi over 2. In this case, it is moved to the right, pi over 2. So instead of starting at the origin, this function would start at pi over 2. We've got 2 examples we will do in class, and I can't wait to do them with you.